Now, heat engines utilize the second law to do work via something called the Carnot cycle. Now, in a heat engine, there is a hot reservoir, and that heat is generated by some means, whether it could be burning coal or oil or a nuclear reaction or wind energy. There are a lot of different ways that heat can be generated, but how it is generated is not important for our current purposes. All that matters is that there is this source of heat, and typically what heat is heated is water. Then the steam will push a piston that converts the heat energy into mechanical work, and then the water or whatever it is passes into a cold reservoir where the heat bleeds out of the substance, and then it goes back into the hot reservoir, and the cycle continues. All that matters for our purposes is that from the hot reservoir, there is some energy coming out of the hot reservoir. We call that QH for Q hot. There is some energy going out into the cold reservoir called Q cold, and the rest of the energy is going out of the system as work. So, we can see that the energy that comes in is the Q hot, and the energy that goes out, some of it goes out as into the cold reservoir, and some of it goes out as work. Therefore, the work done by a heat engine is, whatever energy goes from the hot reservoir, or whatever of the energy from the hot reservoir that does not go into the cold reservoir is then the work done. This is the important equation here. The efficiency of a heat engine is what fraction of this Q hot is actually used for work. So efficiency is E. That's equal to work over Q hot, which could also be written as Q hot minus Q cold over Q hot, which can also be written as 1 minus Q cold over Q hot. And these two are exactly equivalent, and which is, depending on the situation, one or the other might be better than the other. E is, the efficiency is typically given as a percent. So that, say if an engine is 35% efficient, it means however much energy comes in from, or comes out of the hot reservoir, 35% of that actually lines up being converted into mechanical work. Now, if there was not this hot and cold reservoir, if there was not this temperature difference, then energy would not spontaneously flow through this part of the cycle, and there wouldn't be any capability to do work. You need, if these two were the same, the efficiency would be 0. There would be no work done. So you need a temperature difference to do work. So let's look at an example here. In a certain engine, we have 2,250 joules absorbed from the hot reservoir. The engine has 15% efficiency. The question is how much work is done and how much energy goes into the cold reservoir. Well, it's pretty simple that our our efficiency, is equal to work over Q hot, and our Q hot is 2250, and our efficiency is 15%, that's 0.15 times 2250 would be equal to our work. And what is 15% of that? Let's see, that would be 10% would be 225, and 5% would be half of that, which is 112.5. So the work done is going to be 337.5 joules. And then how much energy goes into the cold reservoir? We can simply apply our other equation, this guy. We know that our work done now is, work is Q hot minus Q cold, so that's 337.5 equals 2250 minus Q cold. Therefore, our Q cold is 2250 minus 337.5, which is, let's see, 0.5, that's 10. Oh wait, that's 9, right? If we get borrowed here, so that's 2, and that's a 4, so that's 1, 19. Wait, what? I can't subtract. Let's see, we've got a 0.5, yes. 9, 4, 10, 5, 2. Oh, wait, it's made a 0 for no reason. That's my problem. Okay. 2, 1, 19. So our Q cold is 19, 12.5, not Celsius, joules. Man, I'm failing there. All right. So that's the kind of question you're going to be asked. Now, this guy named Carnot, I mentioned the Carnot cycle. This whole thing is called the Carnot cycle. Carnot came up with this theorem. Carnot's theorem is that an engine with a reversible process is most efficient. And also, a reversible engine's efficiency depends only on temperature. So this is his theorem, and then some calculations involving entropy and calculus, which I will not get into because, well, you don't need to know them. It shows that in the ideal situation, the ratio of the energy flowing into the cold reservoir versus the energy flowing into out of the hot reservoir is equal to the ratio of those temperatures. Okay, so therefore the maximum efficiency of the Carnot cycle. Remember our efficiency. One way of writing it when I factored it. Where did I write it? There it is. The efficiency is 1 minus Q cold over Q hot. Well, we're in that Carnot limit at 1 minus Q cold over Q hot. The maximum efficiency then is 1 minus T cold over T hot. So the maximum efficiency is not 1. Okay? I suppose in theory if you could create 0 Kelvin, then that would be true. These temperatures are in Kelvin. But the efficiency of the engine, even in the ideal case, is limited by the ratio of the temperatures of the hot and cold reservoirs. So clearly, the smaller this is and the larger this is, the more efficiency you're going to get out of an engine. You want the cold reservoir to be as cold as possible, the hot reservoir to be as hot as possible. Practically, there is a point of diminishing returns, because if you're using so much energy to heat up the hot reservoir, then you're not really getting much out of, you're using up all that energy to heat the cold reservoir, and you're using up energy to cool the cold reservoir, and so you don't wind up with that much energy that is able to do work. But ideally, it's better to have a hotter hot reservoir and colder cold reservoir, as you might guess. Applying this result, we know that efficiency is also equal to the work done over Q hot, which means that the maximum work done would be equal to the maximum efficiency times Q hot, which is 1 minus T cold over T hot times Q hot. So that is the maximum work done. And again, if these temperatures were the same, then that would be 1 minus 1. The maximum work we could get out of our engine would be 0. Now, note that for a given temperature difference between the hot and cold reservoirs, it is better to be cold i.e., if our well, we can't do 0, but say we had 50 Kelvin at the cold reservoir versus 150 Kelvin at the hot reservoir, that's going to be a smaller number than if we have 150 over 250, for example. Same temperature difference in an absolute sense, but this one is a third, while this one is whatever it is, 15 over 25 would be 3 over 3/5. So this one is going to give us a smaller number, which will give us an efficiency closer to 1 than this one. So it's better to have it, for a given temperature difference, it's better to have it colder. Just run another quick example here. Find the maximum work done by an engine where the hot reservoir is at 350 Kelvin, the cold reservoir is at 270 Kelvin, if 22 kilojoules come in from the hot reservoir. Well, the maximum amount of work done, simply that equation. So the maximum work done by this engine is 1 minus cold reservoir, 270 over hot reservoir, 350, times 22 kilojoules, 22,000. So what, this is 8 over 35 times 22,000, and I'm not going to bother doing that by hand. That comes out to 50, 28.5, etc. joules of work done by this engine.